Hello students, welcome to class 12 physics class after half yearly exam. I hope everybody will be fine. So today we start a new chapter, electromagnetic induction. In class 8 you studied little bit in class 8 and 10 also, I think a little bit about the idea about this electromagnetic induction, what is induction, you know these things, but in class 12 you uh, know in details, many laws are there, many things is new in this chapter. So before we started the main topic of this chapter, that is induction, before that induction we discuss a very important topic related to induction. That means which is the cause of that induction, that is magnetic flux. So first of all, we have to understand what do you mean by magnetic flux. We know that magnetic field, we know what is magnetic field, similar to the electric field. So magnetic flux is a total number of magnetic field lines. Magnetic field lines are the imaginary lines which is started from North Pole and ended at the South Pole. Okay. And the magnetic field, the field or space around the magnet within which we can experience its influence. That is called magnetic field. The field exerted by the magnet. It has certain limit. Now the magnetic flux are the total number of magnetic field lines or magnetic lines of forces crossing the surface, any surface placed in a magnetic field. Okay, normally we know the definition of electric flux, the number of electric field lines passing through the surface, any closed surface, any surface, normally that is called electric flux. Similarly here, the magnetic flux through any surface, and that surface must be placed inside the magnetic field. And the total number of magnetic field lines or lines of force crossing this surface normally or perpendicularly is called magnetic flux. It is measured as the product of the component of magnetic field normal to the surface and the surface area, because when we discuss the surface area, we know that surface area always perpendicular to the surface, and sometimes the surface which is inside the magnetic field, it is not in a perpendicular, it also makes, sometimes it will make one angle. Okay, so in that time we choose a component of that magnetic field which is directed along the area vector, and if we multiply that two component, we get the magnetic flux. You also see this in this two diagram, the figure A, the magnetic surface also be in a perpendicular, held perpendicularly with the magnetic field. So the magnetic field lines and the area vector are the same direction. So in this case, we did not take any component of the magnetic field. But in case of second figure, figure B, you see that the surface makes some angle theta, with the magnetic field. So the area vector along that perpendicular, and the B is not, the magnetic fields are not along the surface area vector. In that case, we choose one component of the magnetic field, either be cos theta or be sin theta. Okay, and multiply it with that area vector, surface area, and we get the magnetic flux. So in for first case, the magnetic flux is denoted by phi, electric flux also denoted by phi. So for first case, the phi equals to normally B into A, because here the B and A are in a same direction, no component we choose here. But in the second case, what we can write, phi equals to B cos theta, because in that case the whatever the angle made with the area vector, that is a base angle, and base angle always be the cos theta. So B cos theta into area vector, that is A. So BA cos theta. And we know that we studied in class 11 the vector, scalar product, vector product. And we know that the scalar product means the cos theta. So BA cos theta, that means we can write in a vector form phi equals to B dot A. B dot A. So from here it is clear that magnetic flux is a scalar quantity. Magnetic field is a scalar quantity. That's why we know that the scalar whatever the scalar quantity, in case of a scalar quantity, we choose B dot product or the scalar product. And this side figure, the any surface, and within that surface we choose one small area vector, and through that small area vector how much amount of or how many electric field lines passes through this one. So we can get the flux or small flux against that small area element, and if we find out the total flux in this closed surface, so we integrate this one, nothing else. Clear? Okay. So everything is, so the net flux through the surface phi, in this case, in the third figure, in this side, the irregular surface, in this case, where we choose the small area vector, so we get the small flux through that area element, and whenever we find out the total flux through the whole area A, that is phi equals to, we integrate this one, phi equals to close integration B dot dA. B dot dA. B and A are the vector. So B dot dA, that means BA cos theta. BA cos theta. Clear? Okay. Now if the theta, the angle between the area vector and the magnetic field, we know that theta equals to 0 degree, then phi equals to B, and theta equals to 90 degree, phi equals to 0. That means if the area vector and the magnetic field are perpendicular to each other, then the no magnetic flux is present. Magnetic flux will be 0. Magnetic flux will be 0. Now if we talk about the unit and dimension of the magnetic flux, as we know that the magnetic flux is a scalar quantity, so its SI unit is Weber. It is denoted by WB. SI unit is Weber, and the CGS unit is Maxwell, or sometimes it is denoted by Gauss into centimeter square. Gauss into centimeter square. So anything you can write, Maxwell or the Gauss into centimeter square. In SI its unit is Weber, and in CGS unit Maxwell or Gauss into centimeter square. And the relation between Weber and Maxwell, 1 Weber equals to 10 to the power 8 Maxwell. Okay, and the other unit also be present, it is not so important. And the dimensional formula phi equals to m L square a to the power minus 1 t to the power minus 2. This is the dimensional formula of the phi. And the other unit also you get Tesla into meter square. Tesla means Newton into meter by ampere, that is equals to joule. That means from one unit we can derive many units. Okay. So this other unit is not so important. You just remember the SI unit is Weber and the CGS unit Maxwell, and its dimension is m L square t to the power minus 2 a to the power minus 1. Okay. Now related to this magnetic flux also be two types. One is a positive, another one is a negative. So when we say that the positive flux and the negative flux, this is not included in your syllabus, but still you have to know about the idea about the positive flux and the negative flux. Positive flux means a normal to a plane can be drawn from the either side. If the normal drawn to a plane points out of the direction of the field, then theta equals to 0 degree. That means the area vector and the magnetic field are in the same direction. The normal, whatever the normal we draw, that is in the same direction. The angle between them is 0 degree. In this case, the flux is taken as a positive. But if the magnetic field is one direction, another, but the area vector is another direction. That means theta equals to 180 degree, and we know that cos 180 degree value is -1. In that case, we take the flux, magnetic flux, as a negative. Okay, clear. So now let's come to the main topic of this chapter, that is electromagnetic induction, and it is introduced by scientist Faraday. So we also discussed Faraday's experiment, Faraday's laws, and many things.